Hello grade 10s, welcome to this series on representing chemical change. In this series, we will investigate different types of chemical change and how we can represent these chemical changes in chemistry. Let's cross over to Diyasha to find out more about the changes that happen in our world.
Do you know that chemical change happens all around you all the time? When you light a candle or make a fire, you are starting a chemical reaction. Chemical reactions get the dishes clean. It allows you to listen to a battery-powered radio. It's even happening while you're toasting your bread. Every breath that you take is a chemical reaction in action. You breathe in oxygen, but what you breathe out is carbon dioxide. If you really start to think about it, the list of chemical reactions that happen every day seems endless, doesn't it?
Thanks, Diyasha. As you can see, chemical reactions do happen around us all the time, but chemical processes are also used in the industry to produce a wide variety of products we use every day. Some of these products that are made go directly to consumers to use. Examples are washing powder, used to clean our clothes, and dishwashing liquid to wash the dishes. But the chemical industry uses chemical processes to make a large variety of solid, liquid, and gaseous materials that are needed to manufacture other products. For example, in the chlor-alkali industry, a solution of salt undergoes a chemical process in large cells to produce chlorine gas, hydrogen gas, and sodium hydroxide, which is used to make soaps. Sulfuric acid is made in huge chemical plants like this one. The sulfuric acid produced is used in car batteries, to make fertilizers, and in the mining industry to process minerals. Ammonia gas is made in reactors like this one from hydrogen gas and nitrogen gas. The ammonia is used to make nitric acid, fertilizers, cleaning products, and some medicines. So, chemical reactions are used in the industry and happen around us all the time. But is it enough to just know that chemical changes happen around us? Let's see what Diyasha has to say.
When you're studying chemistry, it is not enough to just be able to see or identify chemical change. You also need a way of clearly describing what is happening during the chemical change. And that is what this series is all about.
In today's lesson, we will represent chemical change and use a reaction equation and learn how to balance chemical equations. With so much chemical change that happens around us all the time, you may wonder, where do we begin? Diyasha will set the context for the next few lessons.
We are going to do a whole lot of experiments with different metals, and then we are going to learn how to write down exactly what is happening during the reactions that we see. The reason why we choose to focus on metals is because so many things we see in the world around us are made up of metals. Every concrete building has a framework of metal supports. Electricity is transported via metal cables. Cars, buses, trains, ships, and airplanes all have a metal shell. And to make all of these things, we use tons of metal every year. To kick off our series, I thought we would explore where we find all the tons of metal that we need to make the metal products that we use. As you know, most metals are found in the Earth's crust in the form of rock, called ore. The metal elements are bonded to other elements to form compounds. As a rule, these compounds are quite complex, so it is difficult to separate the pure metals from their compounds. Did you know that South Africa is a world leader in the field of separating metals from their compounds? Our scientists have developed some cutting-edge chemical processes that are used to extract metals from metal ore. For the rest of this lesson, we will look at some of the chemical reactions that take place during the process of extracting iron from iron ore. Let's start by looking at a basic diagram of how this process works. The key steps in the process are: number 1, the ore is dug out of the ground and brought to the surface. Number 2, the ore is crushed into very small particles. Number 3, the ore undergoes special chemical reactions to extract the metal elements. Number 4, the extracted metals are purified. Number 5. The purified metals are used to manufacture different products. But remember, because we are busy with chemistry, it is not enough that we are able to identify that chemical reactions are used to extract the metal, but we also have to be able to represent the chemical change that we see. So, how do we go about doing this? By writing chemical equations, of course. The best way to describe what chemical equations are is to think of them as a special code that scientists have developed over many years to explain and describe what exactly is happening during a chemical reaction. This code uses the symbols we find on the periodic table and the rules of chemical bonding to represent the formulae for the compounds and molecules that take part in a chemical reaction. An important rule to keep in mind when writing chemical equations is that things don't appear from nowhere and they also don't disappear into thin air. So, when you're writing equations, you have to make sure that you start with the same number of elements that you have at the end. This could be in a different combination. This is called balancing an equation. This rule has been stated as a law. It is called the law of conservation of mass. The law of the conservation of mass states that in a chemical reaction, matter is neither created nor destroyed.
In the series on physical and chemical change, you saw an experiment which proved this law. Let's see John perform this experiment again.
Have a look at the apparatus I've set up here. I've got some copper carbonate in this test tube, and I'm going to seal the test tube with this stopper, tightly sealed. I've got some plastic tubing connected to a syringe. No gas can escape from this. It is a closed system. I'm now going to find the mass of the whole system by placing it on the triple beam balance. I found that the mass of this system is exactly 46.5 grams. Take note that the plunger is exactly on the 5 milliliter mark. Now watch what happens when I heat up the copper carbonate. The copper carbonate decomposes to form copper oxide plus carbon dioxide. Now look at the plunger. Can you see that it has moved out? The expanding carbon dioxide has pushed the plunger out. Now let's measure the mass of the system, and it hasn't changed. The final mass of the system is still 46.5 grams.
Do you remember the reactions of how copper is extracted from malachite or copper carbonate? Let's just recap these. When green malachite or copper carbonate is heated, it decomposes and forms black copper oxide, and carbon dioxide gas is given off. The black copper oxide is then heated on a block of charcoal, which is carbon, and copper metal and carbon dioxide is produced. You should remember that in the series on physical and chemical change, we wrote word equations for these reactions. We represented the decomposition of copper carbonate in a word equation. Copper carbonate, solid, forms copper oxide, solid, and carbon dioxide, gas. We represented the formation of copper in a word equation. Copper oxide, solid, when heated with carbon, solid, forms copper metal, solid, and carbon dioxide, gas. How do we translate these word equations into chemical equations? Let's cross over to Diasha to see how iron is produced in a blast furnace and how to write balanced chemical equations from word equations.
All right, now we are ready to take a look at what happens in a blast furnace. A blast furnace is a giant oven that is about 30 meters tall. It is made from steel and lined with fireproof bricks. These bricks trap the heat inside the furnace, where temperatures often rise to over 1000 degrees Celsius. In the first step of this process, iron ore, coke, and limestone are mixed together. You may be thinking that this is a waste of good cold drink, But the coke used here is made from coal and is almost pure carbon. Iron ore, called hematite, contains the compound iron 3 oxide. We can write the formula for this compound as Fe2O3. This tells us that there are 2 atoms of iron bonded to 3 atoms of oxygen for each particle of iron 3 oxide. It is very important to remember that in this compound, the iron and oxygen atoms are always arranged in exactly the same way. The ratio of iron to oxygen is always 2 to 3. The formula is always written in the same way as Fe2O3. This must never be changed. In other compounds of iron and oxygen, like ferrous oxide, the combination is different, and so the formula is different. Here, 1 atom of iron combines with 1 atom of oxygen. This compound has a formula of FeO. Now, let's get back to the process. This mixture of coke, limestone, and iron ore is poured into the top of the burning blast furnace. Hot air is then blasted through the mixture, making it glow white hot. There are a number of chemical reactions taking place inside the furnace. Let's look at some of the chemicals that are reacting and what the products are that are formed. Firstly, carbon reacts with oxygen from the hot air that is blasted into the furnace. The carbon and oxygen combined to form a compound, carbon dioxide. The carbon dioxide formed in the furnace undergoes another chemical change. The carbon dioxide reacts with the carbon in the mixture to form a different product called carbon monoxide. The iron ore, which is mainly iron 3 oxide, reacts with the carbon monoxide to form molten iron and more carbon dioxide. The molten iron trickles down to the bottom of the furnace where it is collected. Most of the iron is taken away while it is still hot and turned into steel. Do you notice that we've already started to represent the chemical changes that are taking place by writing down the word equations? Whenever you are asked to write an equation, this should always be your first step. The next thing we have to do is to translate these word equations from English into chemistry. Let's start with this equation. The symbol for carbon is C. The symbol for oxygen is O. Is there a warning bell sounding somewhere at the back of your head? There should be. What do we know about the non-metal gases of groups 6 and 7 on the periodic table? That's right. In their elemental form, they exist as diatomic molecules. That means that we need to represent oxygen as O2. These elements react to form carbon dioxide. The formula for this compound is CO2. Did you see the clue in the name? The suffix di means 2, so we know that there must be 2 oxygen atoms in the formula. Now that we've completed the translation, we have a scientific representation of the reaction that took place.
Thanks, Diasha. There is just one more thing that we have to add to our chemical equation, and that is the subscripts that tell us what phase of matter each substance is in. So, carbon in the form of coke is a solid. The carbon reacts with oxygen, which is a gas. These two reactants combine to form carbon dioxide gas. Let's cross back over to Diasha to find out how we can make sure the equation is balanced and that mass is conserved during this reaction.
To be absolutely accurate, we have to make sure that we followed the law of conservation of mass. The easiest way to do this is to draw a picture. I'm going to start by drawing a line through the arrow so that I can separate the reactants from the products in the reaction. Next, I will use circles in different colors to represent the different elements. So, one red disc represents one carbon atom, and one blue disc represents one oxygen atom. In this reaction, I have one carbon atom and two oxygen atoms. I now have the same number of oxygen atoms on the left of the equation and the same on the right. This equation is already balanced. Do you see that we have not created or lost any matter during the representation of this reaction? I'm pretty sure that you can figure out for yourselves that not all equations will be this easy to balance.
Well, that equation was certainly not too difficult to balance. Let's try balancing another equation of one of the reactions that happens in the blast furnace. Iron 3 oxide and carbon monoxide react to form iron and carbon dioxide. Try to balance this equation on your own first. To help you, Diasha has a couple of tips.
Firstly, you should remember from earlier in this lesson that the formula for iron 3 oxide is Fe2O3. And secondly, you must remember that you can never change the ratio of a formula to balance an equation. This means that you cannot mess about with these small subscript numbers. But you have to add a whole particle or molecule to balance the equation. You indicate the number of particles you'll need by writing a large number in front of the particles, here. If there is nothing written in front of a particle, a 1 is always implied. So, iron 3 oxide is written as Fe2O3. Carbon monoxide is written as CO. Iron has the symbol Fe, and carbon dioxide is CO2. Next, we check to see if the equation is balanced by counting the number of atoms of each element that act as reactants and the number of atoms of each element in the products. It is always a good idea to record this type of data in a table. Here is mine. As you can clearly see, this equation is not balanced. We don't have the same amount of atoms of any of the elements at the start and end of this equation. The law of conservation of mass is not obeyed. Okay, so how do we fix it? Remember, the one thing we cannot do is to change the formula of any of these substances. The only thing we can do is to show that a different number of molecules are reacting. We do this by writing a number in front of the formula. At first glance, it looks like we need to double the number of oxygen atoms in the product by placing a 2 in front of the CO2. Now there are 4 oxygen atoms on each side of the equation, but this has caused the number of carbon to change to 2 as well. To balance the carbons, now I need to place a 2 in front of the CO. But this changes the number of oxygen atoms again. This strategy is obviously not working. Let's start again. Have a careful look at the oxygen atoms on the left-hand side. Notice that the oxygen atoms are found in 2 compounds, 3 with the iron and 1 with the carbon. On the right-hand side, the oxygen atoms are only found in the carbon dioxide. Since carbon dioxide is CO2, there will always be an even number of oxygen atoms in the product. This means we need to find a way to get an even number of oxygen atoms on the left-hand side. This was the hint I gave you at the end of the last lesson. If we add 3 carbon monoxide particles, this means that there are now 6 oxygen atoms on the left-hand side, and to balance this, I must write a 3 in front of the CO2. 3 times 2 is 6. See, the oxygen and carbon atoms are now balanced. What about the iron? There are 2 atoms of iron on the left and 1 on the right. Balancing this is easy. We just write a large 2 in front of the Fe. This gives us a balanced chemical equation that represents the chemical change taking place inside the blast furnace. Even though that was quite tricky, I'm sure you got the right answer. We will be practicing the skill of writing balanced equations throughout this series, so don't forget these 2 golden rules. Never change the formula of a compound And always check that the number of atoms of each element before the reaction is the same as the number after the reaction.
Thanks, Diasha. That was quite a tricky chemical equation to balance. Just one last thing to make sure our representation is accurate. Remember to add the phase of each substance. So, iron 3 oxide, which is a solid, reacts with carbon monoxide gas to form iron, which is a solid and carbon dioxide gas. Since balancing chemical equations is such an important skill, we will look at more examples in the next lesson when we investigate the reactions of metals in oxygen. Practice this skill in the task video on representing chemical change and visit the Mindset website www.mindset.co.za/learn. Join us next time. Until then, goodbye.